It used to be that when you bought a new computer, it would be twice as fast as your old computer. That doesn't seem to be happening anymore. There is actually a reason for that, and it has to do with the speed of light. Stay tuned and you'll find out what that reason is. Computers are limited by the speed of light, but how? Computers aren't mechanical devices with moving parts. What does the speed of light have to do with computers? It turns out the speed of light isn't just a limit to how fast an object can move through space, but also a limit to how fast information can be sent. To understand how this limit affects computers, let's take a quick look at how computers work. A computer stores and processes information in binary form. This means the information, be it a number, a string of text, an image, or a video, is encoded using just the digits 1 and 0. In the actual hardware, the digit 1 is represented by a high voltage, while the digit 0 is represented by a low voltage. Another way of looking at it is that 1 represents a closed circuit or a switch in the on position, while 0 represents an open circuit or a switch in the off position. Information is stored in registers consisting of multiple binary digits, or bits. Imagine that each bit in the register is a light bulb that is on when the bit is 1 and off when the bit is 0. The central processing unit reads information off one or more registers, performs an operation, and then writes the result back to another register. For example, let's say we have 3 registers with 2 bits each. We also have a chip that adds the numbers stored in the first 2 registers and writes the result to the 3rd register. The first register is initialized to the number 2, which is 10 in binary. The second register is set to the number 1, which is 01 in binary. The contents of the 2 registers are fed into the adder chip, which then writes the value 3, which is 11 in binary, to the 3rd register. The first question that we can ask ourselves is how many operations can this computer perform per second? The output of the first operation, which is now written to the 3rd register, may be used as an input to another operation. Therefore, any future operations following the addition may only be performed after the adder chip has finished computing the result and writing the output to the 3rd register. The actual number of operations that are performed per second is controlled by an internal clock that emits a pulse at regular intervals. The frequency of the pulses is called the clock frequency, and this frequency has to be selected such that every chip has finished performing its calculation and has written the result to its output register. The clock frequency is the primary factor that controls the speed of a computer. One way to increase the speed of the computer is to increase the clock frequency. But in order to do so, the chips performing the calculations have to be redesigned such that they complete the calculations in a shorter amount of time. But how do we do that? It turns out the bottleneck is actually the amount of time it takes for electrical signals to travel from the input registers through the chip and to the output register. Electrical signals travel through conductors at approximately the speed of light. Therefore, the time it takes for the signal to travel through the chip is dependent on the size of the chip and the length of the connections. The larger the chip is, the longer it will take for it to complete a calculation and write the output. But why do electrical signals travel at the speed of light? And what do we even mean by the word signal? What's actually traveling? To understand what an electrical signal is, imagine a simple circuit consisting of a battery, a switch, and a light bulb. When the switch is closed, the voltage of the battery is applied on the circuit. However, current doesn't start flowing through the entire circuit at once. It first starts flowing in the wire near the switch before it starts flowing in the bulb, which is further away from the switch. Imagine that closing the switch creates an invisible wave that travels through the wire. Electrons only start moving when this wave passes through them, and hence the bulb only lights up when the wave reaches it. This wave is an electrical signal, and it travels at the speed of light because that is the maximum speed at which an effect can propagate through space. It is important to note that the speed of electrical signals is not the same as the speed at which the electrons are traveling. The drift velocity of electrons is actually very slow, much slower than the speed of light. However, the signal is what causes the electrons to start moving, and it is this signal which travels at the speed of light. Any changes to the voltage that is applied on the circuit creates an electrical signal that propagates through the circuit and changes the velocity of the electrons in the wire as it passes. When the switch is opened, the current doesn't stop flowing throughout the entire circuit at once. Instead, an electrical signal is created that travels through the circuit, which carries the information that the switch was opened. The electrons only stop moving when the signal passes through them. Likewise, the bulb only turns off when the signal reaches it. To see how this applies to computers, imagine that each bit in the input registers is a switch and each bit in the output register is a light bulb. When the values of the input registers are set, that is when the switches are closed or opened, an electrical signal is created that travels through the chip to the output registers. The bulbs at the output register only light up when the signal reaches them. This delay, caused by the finite speed of electrical signals, isn't the only delay. However, it is a physical limit that restricts how fast a chip of a given size can be. It is impossible to make electrical signals travel faster than the speed of light. The only way we can decrease the time it takes for the chip to complete the calculation is to decrease the distance over which the electrical signals have to travel. We can only do that by reducing the size of the chip. And that's exactly what we've been doing throughout the past few decades. CPUs have been getting smaller and smaller with each generation, thus allowing the clock frequency to be increased. The reduction in chip size has been made possible by reducing the size of the individual transistors making up the chip. However, we've now reached the point where the size of an individual transistor is approaching the size of a single atom. This means we can no longer make our chips smaller, and thus we cannot increase the clock frequency any further. As a result, our computers aren't getting the same speed increases that we've been used to seeing over the years. Thank you for watching till the end, and I hope you enjoyed it.